Hi, in this video, we're going to have a quick review for lithographic process. To begin with, we've discussed about the critical dimension, that is K1 times lambda, but divided by numerical aperture. To make the critical dimension smaller, we shrink the lambda into extreme. We have shrink the lambda on up to the extreme ultraviolet. Moreover, we have shrink the K1 factor such as applying the off-axis illumination. With those, with the processes, uh, we also we also use the holistic lithographic process. That is, not only the lithographic process, but all the processes are fine-tuned to get the better image. Moreover, we have discussed about the multi-patterning process such as LELE processing or self-aligned double or quadruple patterning. However, these litho-etch processes or self-aligned processes make the usually make the baking um, they tend to make the cost more even expensive. So, that is why EUV processes are currently used in modern devices. This is the this is the sample simple how the EUV devices work with the tin bubbles are drop drop inside with the CO2 laser hits the tin bubble. The EUV laser is the EUV is made into a fine laser with the optical system. As you can see, the EUV process is important to uh, to make the modern devices cheaper than cell phone processes or LELE processes. Now let's move on to the etching process. Etching process is etching process is easily to remove the unwanted material from the base. Uh, this is a sample of the etching process. We cut down the unwanted banderole to make the fine pattern. That is the goal of etching. Uh, there are some there are some kinds there are some etching targets such as silicon itself, silicon nitride, and metals. Uh, for example, the silicon itself is etched to make the structure such as fins. This the oxide is also etched to remove the oxide layer such as the natural oxide, the native oxide. The silicon nitride also can be etched to that is used such as spacer, and also metals can be etched to that is unless they are on the contact or metal wires. There are some figure of merits on etching process. First, first etch rate is the speed, how much the etch is done. Second, uniformity means the how even the etching process is done. Next, etch profile. The isotropic etching profile is like etching in like hemisphere profile to make the 3D that is usually used in 3D making 3D structures, and an isotropic etching profile is usually used to make the deep trench such as pigments. Last but not least, etch sensitivity is also important to only etch down the wanted material than unwanted materials. First, let's look let's look about the etching rate and uniformity. First is the etching rate with time and temperature. With the temperature is getting hotter and hotter, the etch rate is higher. Also, as the time flows, the etch depth is usually higher, but unlike this, some etch materials can look like this exponential profile or logarithmic profile. Next, on the right side, you can see the deformity pattern. As you can see, the center of part is much etched than on the outers. Next, we are going to discuss about the anisotropy. As you can see, this is the isotropic edge because the edge through it looks like the hemisphere rather than this vertical. If the edge down profile is vertical, it is like anisotropic edge, and if you can see this hemisphere like structure, you can see it's much like isotropic. Uh, if it's if the profile is fully isotropic, the AF, the degree of isotropy is 0, and if the edge profile is perfectly anisotropic, you can tell that the degree of isotropy is 1. Next, let's move on to the edge selectivity. Edge selectivity is also important because we don't want to edge through the unwanted material. Because if we edge through the unwanted material, the structure can be destroyed. For thin-bed structures, anisotropic etching is what is usually used, but for another 3D structures such as gate-all-around structures, we can also use the isotropic etching method to make these bridge-like structure. Let's move on to the way how the etching process is done. First, we're going we, even though we're going to discuss about this later, but in short, wet etching process is cheap, simple, fast, but it is hard to control. To stop the etching, start or stop the etch twice, start or stop the etch, and the profile of edge is normally isotropic. On the other hand, the dry edge process is cost a lot because they usually use the plasma devices, but this is widely used to make the anisotropic etching process, and and it is easy to control, but the process and the device for dry etching process much much more expensive. Thank you for listening.
Okay, let's move on to the wet etching process. Wet etching process uh, has uh, has three processes to uh, to to apply the etchant to the surface. The use the chemical to etch the etch and leave and finally remove the byproducts from the surface. These not only wet etching process, but also dry etching processes has the processes have these three processes. For wet etching process, the etch rate is largely affected by temperature, the concentration of etchant, and so on. The wet etching processes has usually high selectivity, and and it's usually isotropic profile, but the process control and uniformity is relatively poor. To etch, to etch the oxide, we usually use the hydrogen fluoride, and not only the hydrogen fluoride, the buffered oxide etchant such as these nitrohydrogen fluorides and so on can be used to to control the etch rate to better the uniformity. However, the buffered oxide etchant, as you can see over here, the etch rate is widely affected by the temperature. The To etch the silicon nitride, we can use the hydrogen fluoride or boiling phosphor AC. To etch metals, we can use acid solutions or aqua regia to etch out the gold and platinum. As you can see, the silicon lattice is not isotropic to all the surface orientation, because the 111 plane is stronger than other plane surfaces. Because of this, the etch out the 111 plane is slower than other planes. Because of this, because of this etching ratio difference, the even with the same etching profile is used, the the crystalline the crystalline weight of the silicon for the silicon wafers when the wafers are made, the orientation of the crystalline structures are also really important to make the better etching process. On the other hand, the dry etching has advantages such as for example, this doesn't handle the dangerous acids and solvents. However, dry etching processes still use the dangerous the acid gas or plasma, but dry etching is way more safer than the wet etching process, and we can choose the profile of etching from the isotropic or anisotropic profile. And because it is easier to control than the wet etching process, the resolution of etching is higher, and the controlling of the etching is much more easier. But the dry etching usually uses the plasma or the gas. It is the devices to etch out is much more expensive. The dry etching processes have the two categories. One is non-plasma based dry etching, and another one is plasma based dry etching. The non-plasma based dry etching usually use the use the corrosive gas such as such as acid, and the plasma-based dry etching usually uses the plasma that is accelerated by the electronic or magnetic force. To begin with, the non-plasma-based dry etching, the the gas form of chemical star or acid is injected to chamber, and the wafer is heated, and because this non-plasma based dry etching uses the corrosive gas or acid gas, the profile is usually isotropic. On the other hand, the plasma-based etching process, it is usually called sputtering. The 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 gas such as argon or the noble gas is given energy to be plasma and accelerated by electric or magnetic field, and it is forced to hit the surface of wafer to cut out the surface. However, the selectivity is relatively low, and because if we put the DC bias to the wafer, the plasma or the residues can be residues can cover the mask when after etchings. We usually use the RF signal to spit out the residues. With the tools with combining the plasma based or non-plasma based the two dry etching process, we can use the reactive we can even use the reactive ion etching. We can use the corrosive gas or acid gas to make the plasma, and that is used to etch out the surface. Because the because the because the plasma itself is made from the corrosive reactive gas, the process speed is higher than the normal plasma-based etching. But if we if we put too much gas into the chamber, the plasmas can can this move can scatter to make the even more isotropic profile. So we can choose the amount of the plasma ions to choose from anisotropic to isotropic profile. As this is the deep reactive ion etching or DRIE process. With the reactive ion etching process, we can make the deep trenches for such as for DRAMs or 3D thin and flash memories. With this, we not only with electronic field, we can even apply this magnetic field to sputter to accelerate the ions more even and much stronger. This is one of these. This batch process is one of the most widely used deep reactive ion etching process. First, we apply the SF6 ion for the reactive ion etching. Next, we cut out the reactive ion and we apply the Teflon-based ion to deposit the Teflon layer, and then again we apply this reactive ion etching and so on. With this, we can make this this wave like deep structure, and after this structure is done, um, we can oxidize the silicon to make the structure even, and after oxidization we remove the oxide layer to make this clean and even structure. This batch process is really widely used to 3D structures nowadays. Last but not least, this is the I'm going to tell you about loading effect. Not only for the amount of the etchant and the wafers, even in one wafer, because the structure inside each chip is different because in one place the structure must be dense, and for another the structure must be less dense. So with this difference of denseness, the for dense structures, the edge ratio is slow, and the places that is not dense, the edge ratio is faster. So with this, we need to because of this effect, the edge ratio in a single chip, the edge ratio is not it can be uneven. For for this reason, we usually put really small amount of gas to make the edge ratio even. Thank you for listening.